right, let's roll. Welcome everyone, and welcome to this joint partner webinar where we have a topic for today, which is unlocking real-time IoT insights with Kafka, CrateDB, and Coreflux. With me today, I have Luis Agudelo, Principal Data Architect at Datapebbles, and Hugo Vaz, the Coreflux co-founder. I am Stefan Assanin, Senior Technical Product Marketing Manager at CrateDB. First, some housekeeping rules. I know there's a chat window, but avoid that. Use the Q&A function in Zoom to send us any questions. We will address these questions in the end of the webinar, and the session will be recorded and shared with all of you afterwards as well. And if you have the time and the will to do, please fill in the feedback survey at the end of the webinar. Today's agenda is we will start with an introduction, talking about who we are, and then we're going to look into who CrateDB is, Datapebbles and Coreflux to know the companies behind this. Then we're going to move on to the challenges of real time and the impact of not doing it right, and of course doing it right as well. We're going to head over to the solution architecture, the challenges and the considerations within. And then we're going to have a demo done by both Luis and Hugo, and we're going to talk about the benefits of this solution. In the end, we're going to have the Q&A. Starting off, I am Stefan Assanin, Senior Technical Product Marketing Manager at CrateDB. I have a background within system development, mainly within IoT area. I've done a lot of years as an IT architect, foremost enterprise architecture. I've been doing some consultancy at Gartner and also solution engineering at VMware for the modern applications. With me today, I have Luis. Luis?
Yes, I am Luis Agudelo. I'm the Principal Data Architect with Datapebbles. I've been at technologies for 25 plus years. I've been in Latin America, US, Europe, and the Middle East, and now more recently in the Netherlands. And yeah, that's me. Hugo, you want to have a quick introduction?
Yeah, so my name is Hugo Vaz. I'm one of the co-founders from Coreflux. So I've been working since roughly 2013 on what is known as Industry 4.0 and IoT. And here I kind of working on finishing what we started on Coreflux since 2023. Don't know what will that be, but we keep pushing. Go back to Stefan, maybe.
Great, thank you and welcome. Thank you for joining, and thank you, audience, also for joining. I see more people are joining while we speak. Let's move on. Talking about CrateDB. CrateDB is known as a distributed database, but has expanded to offer a unified data layer as a managed service on AWS, Azure, and Google Cloud as well. It is built for scale, speed, and flexibility. It combines the SQL familiarity with NoSQL agility to handle massive real-time data. It supports all possible data types, including structured, unstructured vectors and time series, delivering the right data in the right time. And from the moment data is ingested into CrateDB, you can run complex, high-performance queries across large-scale data sets. You can use the full text search to organize, search, and analyze unstructured content, or apply the vector search to capture meaning and context from images or text for your machine learning powered applications. Or you can combine them with hybrid search to get the speed of vector search with the flexibility of traditional search. And because it's all powered by native SQL, your teams can work across data types without specialized skills, which then will reduce complexity and resource dependency. At CrateDB, we work hard to ensure that CrateDB has a good integration ecosystem and partners where we together can give you full control so that you as a customer can future-proof your analytics, search, and AI investments. And that's why I'm happy to have both Datapebbles and Coreflux here today, and I will hand over to Datapebbles.
So yeah, Datapebbles is a professional service organization. We're basically a bunch of engineers, and our mission is to fuel innovation with data and AI. So we do everything around the data, including unifying it, architecting it, making sure it's scalable, modular, and is designed for growth, to prepare it also for AI. And we cover everything from generative AI, machine learning, custom AI solutions as well. Everything data ready to make sure it's future-proof. So that's us. Hugo, do you want to have a quick introduction about Coreflux, please?
Yeah, thank you. So Coreflux is basically a tech stack for IoT. So we started as an MQTT broker as our standard and the main infrastructure. So in a sense, we can grow from 1 to 5 million devices as a cluster, either if it is edge or cloud or even on-premise. Since we came from the shop floor, from energy sector, we are able to integrate a lot of different devices. So we translate from typical OT devices like PLCs or even solar inverters, and we bring that into play, that data, and we transform it inside the broker with our language of things. So we are able to automate, we are able to transform, aggregate, so we are able to change that data inside the broker itself. And this provides a full system that you're able to integrate a lot of systems like Kafka, for instance, and even CrateDB directly. So we are able to provide a way to stream data into the databases itself. So we have connectors from one side to the other. So we are the main pipeline. We are scalable, we are modular, and above all, we are secure. So we can also help out on protecting the devices that clearly on the OT side are not made for protection, even on the brownfields. So what we're bringing into play is a full tech stack to bring a data pipeline into place. So
great. Thank you, Hugo. Thank you, Luis, and thank you for presentations. Let's move on to look at the challenge of real time and the impact of not doing it right. And I think, can you take this, Luis, maybe?
Of course. What I'm going to say is a little too obvious for most of us, but yeah, what are the scenarios where the cost of not doing things right will be expensive? So, of course, in a financial world, if you spot a fraudulent transaction after the transaction took place, it's already too late. I mean, you're already incurring the cost, and it's already a big impact. Or what happens if you update the stock after someone places an order online? You realize you no longer have the item that you're supposed to deliver. So that, of course, comes with frustration because, yeah, you might not be able to fulfill the order or need to procure it again, perhaps even at a different price point. Or what happened in the IoT scenario, if you generate an alert after something already happened, it's outdated, that's basically not effective. So could you please move to the next slide, Stephen? And yeah, here I apologize for a little bit too overdramatic picture of a factory already caught fire when some person is looking at the green dashboard still with just an alert. So you get the message here is, yeah, you don't need to have the right data, make the right decisions, but you need to make them timely, because any delays basically mean insights will be outdated, irrelevant, and ineffective. Certain industries, of course, such as finance, healthcare, energy, and anything basically that requires a lot of IoT, of course, kind of falls into this scenario of like real-time decision making. Can you move to the next slide, please, Stephen? I'm going to walk you through a business case. If we move to the next one, please. This is something we built for a leading energy provider. And the challenges they face is they have a lot of legacy systems that couldn't really handle real time properly. They had scalability issues, and they're growing significantly. And they needed also automation and AI in order to help with predictive maintenance and performance optimization scenarios. So they, of course, need to make the real-time improved decision-making, and they make it, they need to be very scalable because, of course, there were big growing ambitions, and they need to make sure they unlock new use cases in terms of providing predictive maintenance, performance optimization, that sort of type of a scenario. If you move to the next slide, I know this is a little bit too detailed, but I'm going to be I mean, it's perhaps a little too small for you to read, but I'll give you an overview of roughly the architecture. On the left hand, we have the plant architecture, so everything physically there. On the right, we have the cloud. Within the plant, we have everything starting with the devices itself, PLCs and all the equipment in the factories itself, in the energy factory. And then we have Coreflux as the MQTT broker, handling all the low latency protocols and all the aspects of communicating efficiently with the machines. So those events, those topics basically get pushed into Kafka, and Kafka in turn basically put this data into the broker, and those get synced into CrateDB at the plant itself. Why we are syncing it directly into CrateDB in the plant is because we had to unlock these new use cases on the plant itself to do predictive maintenance. And basically, we can do all these AI scenarios directly on the plant without having to wait for the data to be flown all the way through the cloud. To complete the journey from the Kafka broker via Mirror Maker, this data is replicated across into the cloud. Sometimes there's poor connectivity between the plant and the cloud, so we needed a very resilient mechanism just to make sure any replay, any data basically gets synchronized whenever connectivity is restored. So yeah, we end up using Mirror Maker for that purpose. And then on the other end, we have another Kafka broker and again, another sync into CrateDB. So here you can have more of a holistic view across all the data across every plant, and you can see basically more holistically what's happening across the entire company. This is a little bit kind of color coded, so any kind of blue sort of boxes is like very core to the data pipelines. Anything green is about network connectivity to make sure every component can see each other. Anything red is more about monitoring, alerting, and making sure like the right people gets notified at the right alert. That's in overall, like the overall architecture. And if we move to the next slide, I'm gonna hand over to Hugo perhaps to describe a little bit more of the big implementation challenges that come with the volumes. We're handling something about up to 80,000 different metrics per second. So yeah, Hugo, I'll let you kind of go through a lot of the challenges.
So thank you, Luis. So basically on this use case, the broker is actually working inside the plant. So we were the first point from edge to cloud, let's say. So we're bringing the information from the IoT devices. So like Luis said, there was a high through output of message that were required, but above all, not only the number of message, but the number of data points that were required. So about 15,000 data points were intended to be collected, and the devices that were being used actually had two protocols that were defined. So it was a Siemens PLC in this case. Not that it matters, but just to check, we maxed it out the number of messages that the device was able to achieve. So this was actually one of the challenges. The translation was not, the translation protocol was not the biggest constraint. The biggest constraint itself was that the device was not able to achieve the number of messages that and the data points that were required to be processed within the broker. Also, this will bring an integration issue because we needed to create this way to compress all these data points, and it was decided by the client itself to compress into one only message, a big one, that was bringing all the data points as a frame. So we needed to handle that. The other point that we had was that the broker needed to be able to receive the same workload for, in some cases, for 32 devices. So not only we had one device that was capable of bringing that information, but the architecture needed to be able to achieve a collection of 32 devices on-prem at the same time. So it brings out a very big data and data pipeline that has an high through output. So another point was that the devices needed to be completely detached from the cloud. So there was a real virtual private network created and defined only for the T device. So the main issue was scalability, because all these current sites needed to be upgraded, and we needed to put this code internally on the devices to send the message. So can you put next slide, please, Stefan? So the solution was using a Coreflux MQTT broker, in this case, connected to the Kafka broker. So Kafka was collecting from a specific topic. And we defined a unified topic structure in order to have all the devices connected within one broker. The device level MQTT integration was the one selected. So we were starting using the connectors from Coreflux, but we decided to go into a full MQTT from device directly sending the message to MQTT. But that brings another consideration to be handled, which is this smart payload transformation. We needed to use what we call language of things, which is LOT, and transform these complex payloads into different message that Kafka will recognize them as data that was able to be ingested on the database. In order to grow, if required, we were able to build per edge location or on-prem location. We were able to build a full out cluster, so we could grow into a standard MQTT broker with a standard MQTT project that was able to translate any location. So we are going to use the same architecture in a way that if you have one device, it works. If you have 32 devices, it also works. So I can show it afterwards, how it's done. But the main idea was to create a deployment that was easy in order to by using other tools like Terraform, to rapid setup what the engineering team required. So in a sense, the project itself, or the architecture that was defined, was standard from cloud until to the edge. The limitation in here was provided by the client, which knows what he's doing with the device itself, and they were able to transform each device to directly send message to MQTT. So the work relied on the devices that they knew, and the rest of the platform was one big project to cover all the plant locations. So maybe the next slide, I can start.
Yeah, absolutely.
Something.
I will stop sharing and you can start sharing, Hugo, okay?
Yes. Send the request. So, okay. So it's already changed. So what we have here is a simple broker. This is simulating what we have on the plant. And we have VS Code. Why? Because the language of things in the broker, they kind of work with VS Code. You are able to integrate a document, and at the same time, you're able to have the code itself. So in a way, we needed to send this a couple of messages that were defined under the standard connectivity from Kafka. And in order to do that, we had one big message that is actually, let me go here, that is actually on the second point, which is here. So the message that was defined was this one. So a very big message with a lot of data points that were being handled. So the PLC itself was sending a message in order to show what the devices had. And this created an issue because we needed to, in a way, divide the payload message. Let me just close here. We needed to divide the payload message into, so this was the message, into chunks of information. So in order to do that, we defined a model that kind of breaks down the message into small parts, which is this one here. So we are able to get the message divided, and afterwards we used regex in order to take the chunks of information that we needed to get from each specific location. So all these big CSVs are here just because it was easy to pack the information because of the high through output. And once we have this divided into, let's say, fields, which were divided here by using regex. So this, the language of things is very similar to English. So we are publishing a topic with a division of BB1, BB2, and so on. And then we use those same topics and we split them into CSVs. So we are able to divide the CSVs into different arrays. So inside the broker itself, you are able to see the arrays divided. So the broker itself picks one message, and with that code, it's able to divide of all the messages that are required. So we kind of get all the informations into chunks of data that then we can map into one single model. So we needed to create this JSON file, and for that we have what we call the models. They work with the JSON and Google and protocol buffers. So you are able to define a model that goes to a topic, in this case Kafka Plus, so it can be Kafka BB1, BB2, BB3. So this is actually using the wildcards, it's a good way to scale the system because you're not only fixed to only one position, you are able to put other devices. So all the code kind of is related to the point of origin. If you create one topic, a new one, something like ZZ1, it will become Kafka ZZ1 with this code. So if you are able to add another device, because this week you needed to add a new battery model, you're able to add them, and the system, you don't need to change the code. So we're able to do that. But in a sense, we are adding a timestamp, we are adding an object, and all the properties that are related to that one by specifying the address. 0, 1, 2 will be DC current, 3, power. So what happens in the end, if I publish, is that you get a final JSON message that Kafka uses, and it's dynamically created for each one of the brokers. So with this information, Kafka receives this and ingests into CrateDB, and I think Luis can show that what he's able to do with this data. So maybe I'll pass to you, Luis.
Terrific. Let me share my screen. So yeah, here, this is just a quick overall dashboard of the live data, as you can see. So there is about 83 million records at the time, and basically we kind of see roughly there's about 10 to 15 kind of queries per second being processed, and the speed in milliseconds is not exceeding, let's say, 8 or 10 milliseconds each. That basically cuts, of course, a lot the time between things being generated. So let's say, for example, I want to query now in Crate directly what data is on the battery rack. So I can just quickly sort of, I don't know, order by time descending. And that's going to basically retrieve the exact data that was actually pulled from the broker. with a very low latency. So from the time actually the signal got produced until the time it kind of get into a first create on the edge and also create in the cloud, I mean, it just a matter of seconds at most. So that's basically what we wanted to show you. Perhaps we can go back to the deck, Stefan, please. So in a summary, I mean, what we managed to achieve is we created a very scalable performance system, using real data by efficiently really communicating with the PLC devices, efficiently transferring the data across, leveraging the power of CrateDB to make sure we unlock some of the use cases in regards predictive analytics, predictive maintenance. And this will basically create a very competitive advantage for the client, because I mean, this is giving them a long-term kind of sustainability, given the fact that you're sort of predicting more efficiently all the data that you already have in real time. I think that's basically what I wanted to say. I mean, anything else, anyone else? If not, we just move to Q&A, I think.
Great. Thank you, Hugo. Thank you, Luis. Let's move to the Q&A, and I have our first question here. Let's see. Says that didn't fully get why it was needed to split up the message into arrays. Could you please elaborate on that? Was it performance problem? If so, where was the bottleneck?
Do you want to tackle that, or?
Yeah, anyone of you.
I can tackle that at least. So the number one issue that we ended up discovering was that we are collecting data, each data point inside the devices itself. So we're going to the memory addresses, so the specific addresses of one for each topic, and we reached the limit of the device itself. So we were never able to pass from 10K message per second, and it was a limitation on the device manufacturer itself. So the way to go around it was that the device created a kind of picture, and since it's very limited in terms of what you're able to do with a PLC, it's not, let's say, an object-oriented device that you're able to create code. It's very limited in terms of the code that you are able to create. And they were able to map all the data into a CSV protocol. So they created a custom CSV protocol in order to put the amount of information that they required. And that was actually a challenge for the integration itself, because each plant, in the end, it was going to be different, and you needed to have like a custom connector on the Kafka side in order to handle this. What we actually did with the language of things was that we received that CSV, and we were able to transform into what we were expecting that the device was able to create. So that array decision actually was not a technical, a good architectural decision that we had to make, was something that we needed to cover because it was a challenge of the limitation of the device itself. And the solution itself was to bring a code in language of things inside the broker that was able to handle any specific device that was being installed by the customer. And we were able to do that. So it was not something that we intended to. It was a challenge that we were able to cross it and sort it out with the broker from Coreflux and with the language of things. So that adaptability was key on this. I hope it answered. If you want to add something, Luis.
Yeah, I'll just perhaps round it up saying, of course, it's easy to forget sometimes, like IoT devices, the main purpose is not generating data, it's actually doing the main business function that they're created to do. So we basically had to be very efficient for them to kind of push all the data, all the metrics out, leaving all the complexities about sort of how to manipulate big streams of data to the broker and the downstream sort of systems, so they can basically spend no effort other than just collecting metrics, pushing them away, and any other transformations kind of happen down the line.
Great, thank you. I hope that answers the questions. Let's move on to a question here. What advantages does Datapebbles offer when paired with technologies like Kafka and CrateDB?
Yeah, we, as a professional service, we normally kind of are technology agnostic, but yeah, we kind of try to choose the right partners for the right solutions. So Kafka basically is becoming very much like the standard when it comes to stream processing. And I think in this particular situation, Kafka was used because we knew beforehand that the connectivity between the plant and the cloud wasn't always guaranteed. There could be big periods of disconnection and sometimes months. And we needed to use kind of this mirror maker kind of facility within Kafka to kind of make sure everything gets synchronized. We could have pushed a lot of these synchronizations to a different type of technology, but we thought like Kafka was best geared to it. Also in terms of scalability, basically Kafka can scale as much as the infrastructure kind of you give them. So this is already proven like a big advantage for reducing, let's say, the time it takes from the data, from the moment data has been generated, and the data actually can be actioned and asked questions about.
Thank you, Luis. Next one here is, what role does Coreflux play in maintaining data integrity and consistency across distributed IoT networks?
So basically, the first, to answer that, first thing I will mention, of course, is the standard. Since we are built on the MQTT standard, already some of the questions that you are saying actually are answered because of the quality of service, for instance, which is something that is already defined on the protocol. So the protocol itself was created in order to maintain a pipeline, to really be able to provide the message with the right quality of service to the ones that are consuming those messages. And that's something that we decided to do, to build our technology on top of the MQTT Broker because of that in the end. And also the fact that we are able to put other solutions besides using normal TLS as security, we are able now to achieve MTLS with our broker. So we build them on top in order to maintain the right and proper streaming of the messages. With Language of Things, we are putting an additional layer on top of that. Since every time an action occurs, it's processed by collecting all the inputs and processing that workflow and providing the outputs as required. So it kind of acts like a PLC that's able to collect in the moment it receives, and then it processes, and then it outputs the message. So in a way, it streams the message on the order of arrival of each message. So we bring an additional layer, a startup layer, let's say a pre-streaming concept into the device, which are not particularly prepared for, like Luis mentioned, they are made to do the specific function. They were built to control a machine. They were built to invert in the energy from DC to AC. So those are the main functions of the device, not to stream data to us. And we enter as the first protocol that's able to collect, aggregate, and transform with a pre-streaming as a pre-streamer processing unit, let's say. So it kind of takes the workload from Kafka and from the producers of data that you typically use in a solution architect like this one. So we bring that into play.
Great, thank you. We have a question here saying this is focused on monitoring only. Want to know if there is any development for security detection use. I understand that the main application of this solution is the energy market. I think.
Yeah, I'll try to tackle that. Yeah, so the first case, of course, yes, was monitoring and making sure the right person gets informed about any type of event. But I think the key thing is, as you know, AI sort of needs lots of data and very good quantity of it. And this is perfect for this scenario. So IoT is sending lots of volumes of data all the time. So the message is this is unlocking a lot of new AI use cases. So you start then create models with that data to understand, I don't know, for example, when you're about to experience some sort of fault, checking the temperature, checking the vibration. Well, there's a few sort of interesting sort of algorithms, but you can sort of start to predict and be more proactive about things that are about to happen, like before they happen. So more moving into the forecasting territory, not just on monitoring and detecting what already happened.
Can I just add something?
Yes.
Yeah, so yes, this is very focused, at least the demo that we made on monitoring only. But in this case we didn't use. But this architecture, with this architecture, you are able also to manipulate what you have on the OT devices. So if there is a business logic on a specific sector, you are able also to achieve, because in our case, we are bi-directional in terms of we are not just collecting, we are able also to act with a rule system that you are able to control. So this architecture, we were also able to go and to tackle a different type of application in the end.
All right. Moving on to the next question. I think all of us can answer, but I think it's nice if Luis can answer this. So which features of CrateDB were the key reasons that it was used in this project compared to other databases?
Yeah, I gladly answer that. We use it mainly two reasons. So a lot of it is time series based. So as a time series database, of course, Crate has the flexibility to be a time series database. But it is like many things under the same roof. It's also a vector database. So it's also, when we talk about these new models for enabling predictive analytics, also you could sort of use this sort of capacity to process models that way. So yeah, we use it primarily as these two forms. I mean, you know, like Crate is pretty much in the intersection between normal SQL, like structured database, and a structured database, and Elasticsearch kind of thing. So we kind of leverage also the fact that it can be time series, can be vector, can be geographic, can be many things under the same roof, but you can still use the standard SQL. So I guess that's sort of the main reasons we end up choosing CrateDB.
Yeah. Hugo, any comments, or I will ask CrateDB comment as well. I think additionally there is these seamless integration with the Kafka, which is also, I think, beneficial for this. So as this is available, it allows the real-time ingestion of data streams into the CrateDB tables, and that together with the SQL and the native SQL interface will then allow for the instant querying and aggregation of data, and especially when it comes to rapid querying on large data sets, as Hugo showed in his part of the demo. Let's see, another question here. How does Datapebbles manage cloud-agnostic deployment across hybrid and edge architectures?
Yeah, here we kind of tend to use best practices in the industry. So yeah, we use Terraform or tools designed to kind of do infrastructure as code across different type of clouds. So I think, I mean, we kind of try to sort of see, use whatever makes sense for the particular client. Definitely, yeah, if we have a a very mixed set of infrastructure, yeah, we'll definitely be looking for things like Terraform to help automate those deployments.
Great, thank you.
I think there is a chat on the chat, a small question.
It ended up there still. Let's see what that's. How do you compare CrateDB with PI Historian? Is that the question to?
I wouldn't know how to answer that.
No, me neither. Me neither. Let's see. Same person also asks, can you elaborate on data engineering activities being done in Kafka CrateDB Coreflux?
Yeah, so that's basically a lot of the stuff we do as Datapebbles. We do data engineering, everything from collection all the way to the model. So I mean, data engineering is a lot of it. So this thing we talk about combining everything into the relevant payloads for the different devices and building the whole infrastructure, the system. That's basically what we do. But yeah, it's all fundamentally a data engineering kind of type of exercise. Here, we wanted to keep the data as raw as possible, because also there is subject to be audited. So yeah, we didn't want to do necessarily a lot of transformation. Sometimes if you do a lot of transformation, you need to preserve basically data as close as possible to the device, because you might even need to use it for like warranty for particular device and stuff like that. So yeah, let's say data engineering is not necessarily the most extensive in terms of transformations, but it's basically more about how do we make the pipeline as efficient as possible, just to make sure like data flows seamlessly between the edge and the cloud.
Great, thank you. How flexible is Coreflux in adapting to different protocols and formats from various connected devices?
So that I can answer. We have what we call connectors. They kind of bring the first layer of translation from whatever to MQTT. So it kind of translates data from like you can check it as like speaking English or Spanish. We kind of translate everything into English. In our case, it's MQTT. So the connectors are kind of working on that. We call them connectors or routes. And then there is another layer which is often forgotten, which is what is the meaning of that data. So you might have one device that is providing you with the Boolean saying true or false, but the same data in another device with the same concept of information, it's 1 and 0. And this is also something that needs to be translated. And it can also be Celsius to Fahrenheit, so it can also be units. So in data engineering activities, especially on the question before, we also do those kinds of transformation while keeping the data with the same time unit in order to be injected into the database. So we also translate data inside the broker to the unit that we want. And in some cases, the data can be provided from one device, but it should not be provided to a specific device. It might be the case that you want to really enforce certain rules. So with the language of things inside the broker, you're able to be flexible on creating that as your own system, as your own, let's say, basis for your own data pipeline. So we are bringing that flexibility with two components. The first one being the connectors and routes, and the second one is being able to change the data accordingly within your broker with the actions and also the models and the rules.
Thank you. I think that will have to be the last question we have today. I want to thank Luis Agudelo from Datapebbles, Hugo Vaz from Coreflux. I want to thank the audience for participating and joining today's webinar. I hope you enjoyed it and wish you a good rest of the week. Thank you.
Bye-bye.
Thank you. Bye-bye. Thank you.